We start with horizons and singularities today and study the local causal structure of space-time. For Riemannian manifolds, the metric defines the shape of the manifold, defines its curvature and so on. Now, on a Lorentzian manifold, the metric defines also the causal structure of that manifold. The metric determines what is time-like, what is space-like, what is light-like. The metric determines in which direction a traveler can travel. Obviously not in a space-like direction. Now, consider an arbitrary point P of the manifold and an arbitrary convex normal neighborhood of that point. Remember what that is. When we studied Riemann normal coordinates, we also introduced convex normal neighborhoods. A convex normal neighborhood of a point in a manifold is a neighborhood in which there exists a unique geodesic connecting our point to any other point in that convex neighborhood. You see, if you take a point and you consider a neighborhood that's too large, it may be that there are two geodesics that get to a point. So a convex normal neighborhood is one in which there's only one geodesic, where it's still unique, the way you go from the reference point to any other point in that neighborhood. There always exists such an, that's a lemma, there always exists such a neighborhood. It may be small, but it always exists. Now, consider a convex normal neighborhood of a point.
Excuse me?
Yeah?
In which sense is it convex?
Well, you can reach every point with a geodesic. You don't have to, so to speak, go around corners there. Let's just consider it to be a composite convex normal neighborhood, just meaning as far as you can drive the exponential map uniquely.
Isn't a convex set one which contains line segments?
Yes, but in this case, you know, with geodesics.
Well, geodesics are lines.
Yes, but I'm not exactly sure whether it matches that definition, so I didn't want to go into that. Yep.
How recent is this result that there always exists a neighborhood around the point?
I don't know.
Because I was looking this up the other day, and there was a paper from 2008 investigating Lorentzian manifolds and the sizes of these.
Yeah. I don't know. I would imagine that it's relatively old. I mean, it's basically the exponential map and its uniqueness. So you should be able to cover that with the theory of ODEs, actually. Yeah. Now, let's consider such a neighborhood. And now, let us consider a point in that neighborhood, a point P. Here, this should be a position variable, so it's space-like. This is a space-like slicing, and here is a time variable. Then, for any event P here, we have a backwards light cone. And I'm indicating it by some sort of a wiggly line because depending on the coordinate system, this doesn't have to be a straight line, and also because of the curvature. So there is a backwards light cone to any event. Now, the laws of nature have to be causal, or locally causal, and that means that whatever happens at that event here should only be influenced by whatever is inside or on the backwards light cone. Things that happen over here should have no impact on the event here because they would have to travel with faster than the speed of light to there. This is a new feature of relativity. Before Einstein, in Newton's model of a universe, there would be no such thing because there is no limit to speeds. Therefore, any event that was prior to this event could have influenced it. But in relativity, there's a backward light cone and it's finite. So what we have is that the equations of motion of matter fields must allow us to calculate the values of the value and derivatives and so on of a field over here on the basis of knowing those only on any one of those slices of the light cone. That must be enough information for it to be causal. You might think, well, okay, that's obvious, but it turns out that it's not quite obvious. For massless fields of spin larger than 1, it's not actually possible to do that in general. You can read up the details on that in the text by Wald on page 375. You can't have an ordinary wave equation like the Gordon equation or like the Maxwell equation, linear equation like that, and have a well-posed initial value problem of this kind. Now, gravity is, of course, described by a massless field of spin 2, which is larger than 1. But then gravity is not, the equation of motion of gravity is not like the Maxwell equation. It's not like the Gordon equation. It's not the linear equation. So that's a non-trivial feature here. And it's interesting to realize that there are actually, aside from gravity, there are no other known massless fields that would have spin larger than 1. Maybe nature doesn't do it because of that obstacle. All right, I made already that remark that in Newton's theory, the data in the backward light cone don't suffice because the speed of light is actually infinite. So equivalently, we can say that the laws of matter fields are locally causal if signals can be sent between events, only if there is a curve between those two events whose tangents are non-space-like. Right? So event Q can influence event P only if there is a path through the space-time that connects the two events where the tangent vector is always non-space-like. So you may travel that path at less than the speed of light, or maybe at the speed of light, but not exceeding the speed of light. So it's not allowed to be space-like. So we want the tangent vector. If gamma is the path, then gamma dot must have a length which is smaller or equal to 0. Equal to 0 means speed of light, and smaller than 0 means time-like, so slower than the speed of light. So again, we see that the causal structure is determined by the metric. The metric determines whether something is traveling faster or slower than the speed of light by taking the tangent vector, plugging it into the metric, and checking whether or not the metric comes up positive or negative. Now you may think, okay, the metric contains all the distance information on the manifold. And as part of that, it also knows when distances are positive and when distances are negative. I mean, distance squares, when they are negative. That's fine, but just knowing whether G is positive or negative is not all that much knowledge. The metric you can actually use to work out exact distances, not just the sign of them, and also angles between vectors. So it would seem that the metric has much more information than just the causal information. Now let us get to the bottom of that. This is going to be a very fruitful exercise because it leads us to Penrose diagrams and a deeper understanding of conformal transformations. Let us work out how much extra information the metric has other than the causal information. So the metric has information in it that allows us to determine whether a vector is space-like or time-like or light-like. What other information on top of that does the metric contain? It turns out very little. If you just know the sign of the output of the metric, you already almost know everything about the metric. So here's the theorem, and you may want to discuss that as part of the essay as well, because it is important in the context of how you can describe the curvature of a space-time. So here's the theorem. It says, assume that on a differentiable manifold M, we don't know the metric. So we can't evaluate G of psi and eta at any point. It's a Lorentzian manifold, and we are not given the metric. But assume that at every point of the manifold, for every tangent vector, we know the information whether or not its length squared with respect to the metric is positive or negative. Okay, so assume that we don't know the metric, but we know the sign of the metric. You plug in any tangent vector at any point of the manifold, and the sign of it, whether it is positive, negative, or zero, that, let's say, we are given. Then, how much do we know about the manifold if we know that? It turns out, and that's the conclusion of the theorem, that this information, just the sign of the metric, already determines the metric tensor up to a conformal transformation. So it determines G mu nu of x up to a scalar function in front. That we cannot conclude. That scalar function we cannot conclude, but everything else is determined already in the metric. By the way, after I gave that lecture in a previous offering of this course, there were two students in the course who came up with some good ideas, and we published a paper on that motivated by this theorem just a few weeks ago. And I'll tell you a little later what it is about. Well, maybe I can already tell you a little bit about it. You see, knowing the sign of the metric apparently gives us already almost everything about the metric. So we thought, consider the propagator. If you're familiar with quantum field theory, the propagator is the two-point correlation function between the quantum fluctuations here and quantum fluctuations there. And we thought, the two-point correlation function between quantum fluctuations here and quantum fluctuations there can probably be used to find out whether two events, the event here and the event there, where you look at the quantum fluctuations, are space-like or time-like to each other. So we thought, maybe on the basis of just the two-point correlator, we can already get to the metric up to a conformal factor, and maybe beyond. And so what we proved is that indeed you can get the metric entirely. If you know the two-point correlation function between quantum fluctuations at any two events in space-time, you can from that alone calculate the metric itself entirely. And the overall idea behind that was this. I think I have the reference to the paper somewhere in the notes. The overall idea was this. In general relativity, we translate the math into physical experiments by interpreting certain mathematical space-time distances as actual physical distances as to be measured by unit rods and times as to be measured by synchronized clocks. But at a level of distances smaller than atoms, we don't really have clocks, nor do we have standard rods. So how do we make sense of GR? How do we make sense of general relativity? How do we translate the math of it into experimental data at such small scales where we don't have standard clocks or standard rods? Or in other words, how do we measure out the curvature of space-time at very, very small scales. All we have there is quantum fields. And so what we showed is that if you know the correlation function between quantum fluctuations of a field and nothing else, just a differentiable manifold, and you have this two-point function on it, you can actually retrieve from that the curvature.
Do you need to know the correlations for all time?
Yes, you need to know them for any pair of points in the space-time, and then you can get the metric everywhere. Actually, you don't only need to know those correlations in the coincidence limit. It doesn't matter what the correlations are between events that are very, very far apart. You only need to know the coincidence limit. Yeah, that was a paper with students in the class. Okay, so the theorem here simply says that if you know the causal structure, if you know where the light cone is, at every point of the manifold, you know the metric up to a scalar prefactor. That's the theorem. Let's prove it. It's going to be very important for visualizing and understanding the structure, the causal structure of spacetimes. Okay, so first of all, let's start with a bit of intuition. What does a conformal transformation do? Well, a conformal transformation multiplies the metric with some scalar prefactor. This will leave lengths and angles invariant. If we define the angle between two vectors in the usual way, irrespective of this being an indefinite metric space, if we define the angle, the cosine of the angle between two vectors in this way, that it's just the inner product between the two and then divided by the product of the norms, then under a conformal transformation, that gets multiplied with a function c, this gets multiplied with a function c, that gets multiplied with the same function c, so we have c over square root of c goes away. Okay? So conformal transformations are called conformal because they keep the angles the same. Now, let's get to the proof of the theorem. Consider a time-like vector xi and a space-like vector eta. Then let's ask whether there are linear combinations of xi and eta that are light-like. Is there always a number lambda such that xi plus lambda eta is light-like? Intuitively, we would expect so, right? Because if xi is time-like, and then we add a gazillion times eta, which is space-like, we expect that it's basically eta now, because the component of xi is negligible, so we expect that that becomes space-like. If indeed, for any pair of vectors xi and eta, time-like and space-like, there is a linear combination such that the linear combination is light-like, then we can assume this lambda to be known, right? Because by assumption, we know the causal structure of the space-time. By assumption, we know where the light cones are. By assumption, we know not the metric, but we know which vectors have negative and which have positive length squares. So, by assumption, we know those numbers lambda. Now, let's prove that it's really true that there always is such a lambda. That's easy. Here is the quadratic equation that we have to solve. The length squared of the vector xi plus lambda eta is given by this. And let's call that function f of lambda. It's a quadratic equation for lambda, right? And so it has two roots, lambda 1 and lambda 2. We know, of course, that they're either both real or both complex. Now, xi is time-like, which means that f of 0, if the eta is simply absent, is negative. On the other hand, eta is space-like, and therefore, if we choose the lambda large enough, the xi becomes negligible, and we have that the f becomes positive. Therefore, it has to go through 0, because the whole thing is continuous. And therefore, the function f of lambda must have at least one real 0. But that means it has two real roots. And both, so this equation has two roots, lambda 1 and lambda 2, and we can assume that we know them. Okay, so knowing the causal structure of a space-time means that we know at every point, for every two vectors psi and eta that are time-like and space-like respectively, what the numbers lambda 1 and lambda 2 are that make the linear combination a light-like vector. In particular, one can prove that the product of those two roots, lambda 1 and lambda 2, gives us the ratio between the length squared of the time-like vector and the length squared of the space-like vector. And if that's true, it means that we can assume that this ratio is known on the basis of just knowing the causal structure of the space-time. So if this is true, I'll show you in a moment how to prove it, then on the basis of just knowing the causal structure of the space-time, we can assume known, we can conclude what the ratio is between the length squared of psi and the length squared of eta for all time-like psi and all space-like eta at all points of the space-time. How to prove it? Well, we take the length squared of the linear combination of the two vectors, where lambda is one of the two roots. We know that that is equal to 0. Let us spell it out. By linearity, we get that g of psi xi, that's this term and that term, plus, and then we have twice the mixed term, 2 lambda 1 times this, plus lambda 1 squared times that is equal to 0. That's the equation that we get when we spell it out for the first root, lambda 1. And then we get exactly the same equation also holding for the other root, lambda 2. So we have two equations here. Both of those equations have g of psi and eta in them. So we can use both equations to eliminate the unknown g of psi and eta. And then we get one equation that relates g of psi xi to g of eta eta. And that equation, I'll leave it to you as an exercise, is this one. It's the one that we were claiming to be true. This one. Okay, so far we can conclude that from the causal structure alone, we can deduce that ratio. The ratio of the lengths of any two time-like and space-like vectors. But from that, we can also deduce what the ratio is between the length squares of any two time-like vectors. Previously, it was just between a time-like and a space-like vector, but actually we can also get those ratios, and also the ratios of the length squares of two space-like vectors. And how do we do that? Well, we know that this is true, where this is time-like and that's space-like. We just proved this. I mean, it's true that we know these ratios, and we know those ratios. So this is one time-like vector and a space-like vector. That's another time-like vector and the same space-like vector. We know these. But since we know those factors here, just from the causal structure, we can now take those two equations, eliminate the g of eta eta, and then get that. So we can also calculate the ratio between the lengths of any two time-like vectors, namely as the ratio of those numbers that all can be determined. Now finally, consider arbitrary non-null vectors, alpha, beta. Then what can we tell about the inner product between alpha and beta with respect to the metric? Well, we can write this g alpha beta as g of alpha plus beta and alpha plus beta minus those two terms. See, there's going to be an alpha term that's taken away by that. There's going to be a beta term in this that goes away with this. And then there's the mixed term, 2 times alpha beta and 2 times g of alpha beta. And if you there's a minus here, there's a minus, I had originally forgotten that one, and then 1/2, so we get g of alpha beta. So that's a trivial rewriting of g of alpha beta. The point, though, is that this has an arbitrary vector here, an arbitrary vector there, and we have so far not learned how to evaluate this on just the basis of the causal structure. But by writing it in this way, we gain that it's expressed in terms of g of twice the same vector, and we have a handle on that, twice the same vector in g, we have a handle on that, and again, twice the same vector in g. We know how to calculate these lengths. Okay, so by the lemma now, by our result here, namely that we can get the ratios between the lengths of any two time-like or space-like vectors, we obtain that the ratio between this value of the metric and the length of a time-like vector is given by all of this divided by the g of psi xi. I'm just carrying this forward here. And you see now we have here the evaluation of the metric on any two arbitrary vectors up to some scalar function here is equal to all of this, where here we have the ratio of lengths between vectors, lengths of vectors, lengths of vectors. You see, this is just the length of a vector in the numerator, length of a vector in the denominator. All of these can be calculated from just knowing the causal structure of space-time. So what we can conclude from this is that knowing just where the light cones are, we can calculate this ratio, that ratio, that ratio, and therefore we can calculate this ratio, where this is the big prize, the metric, evaluated for two arbitrary vectors, and here is some other function that we do not have a handle on. So what we get is the metric for two arbitrary vectors alpha and beta is given by stuff that we know times g of psi xi. And g of psi xi is an unknown scalar function. So the conclusion is, if it is known which vectors are time-like, space-like, or null, then it is possible to calculate g of alpha beta at all points of the manifold for all alpha beta in the tangent space up to a scalar prefactor. And that was the claim of the theorem. This means that the causal structure alone already determines the angles between vectors precisely. And it determines the lengths of vectors up to a positive scalar function. So for an individual vector, of course, it means nothing. But if you have like 5 or 100 vectors, we see here that the causal structure alone determines the length up to a scalar prefactor that is the same for all vectors, right? So it's still a very stringent finding. Okay, and here is the reference to the paper that I wrote with two previous students in this course, where we basically extend that to where we are saying the input is not knowing the causal structure of the space-time, but the input is the two-point functions, the two-point correlators, the correlations of quantum fluctuations. Now, a key implication of this is, I mean, on one hand, it's interesting because it tells us that we can describe the curvature of a space-time in yet another way. there's the metric, there's the affine connection, the spectral geometry and efficiency angles and so on. But yet another way to describe the space-time's curvature is to give its causal structure plus a conformal factor. Now this theorem also has very useful applications. Consider this implication. Two spacetimes given by the same differentiable manifold but with two different metrics on them, for which one metric is obtained from the other by just multiplying with a scalar prefactor, phi, those possess the same causal structure. Which means that spacetimes fall into conformal equivalence classes. Two spacetimes are conformally equivalent if there exists such a function phi that relates their metrics. Now this is very useful to help intuition. The spacetimes that we are dealing with to model our universe are usually infinite in size or at least very large. It's very difficult to draw them, to sketch them, to get a hold of the causal structure in there, just because they're so large. Now, conformal transformations can be used to shrink stuff, to make it very small, make distances smaller, because they multiply the metric, which determines length. And this theorem above tells us that we can do this without disturbing the causal structure. For any space-time that we may actually be interested in, we can consider a space-time obtained by multiplying it with a conformal function in front of it, in front of the metric, which will have the exact same causal structure, but maybe much smaller. Maybe even so small that it's finite. And we can draw it on a little piece of paper. And in particular, we can arrange it in such a way that the angles, if we draw light cones at 45 degrees, this is still the case. So that we have our space-time in principle is very large, and the light cones in the space-time diagram are 45 degrees. We can shrink all of this and still keep the light cones at 45 degrees. The main application of this is Penrose diagrams. Let's start with the simplest case. So the idea of Penrose diagrams is to do exactly this. Take our infinite space-time and shrink it through conformal transformations while keeping the local causal structure. Let's start with the simplest example, Minkowski space. So M is just R4, and this is the usual metric eta. And that would be the usual way of writing the metric in Minkowski space. But let's change to spherical coordinates. It's exactly the same Minkowski space then, but now the metric is written as minus dt, the tensor dt, dr, dr, and then r squared times this spherical measure of the metric. The time variable is still running from minus infinity to plus infinity for the infinite future. R is now a radial variable, which runs only from 0 to plus infinity. Phi is an equatorial angle, and theta is a polar angle that gets you from the North Pole 180 degrees to the South Pole. So these are two completely equivalent descriptions of the same space-time. It's the same differentiable manifold, the same metric. It's just Minkowski space. Now, let's look at a different space-time. A different space-time which is given by some differentiable manifold m bar, not the same as our m here, differentiable manifold m bar, and a metric g bar. And the metric is given by this expression here, which is similar to our Minkowski space in spherical coordinates, but it's not quite the same. You notice that here we have a sine squared of r bar squared, rather than just an r squared. And we have this funny restriction here on how far the t bar and the r bar can go. Particularly the r bar is again positive, just like a radial variable is supposed to be. The t bar variable can range from minus pi to pi. And the phi and the theta, again, behave just like angular variables would do, equatorial and polar ones. Now it turns out that the two spacetimes, Minkowski space and this spacetime, are really different. You cannot obtain the one from the other by change of coordinates. But they are but they have a nice, interesting relationship between another. And that's because if you map the variables t and r and theta and phi into the variables of our other spacetime here with this transformation, which is nonlinear, and never mind the details of it, it's not so important exactly how they work. But if you do map, if you take the diffeomorphism that maps the coordinates of Minkowski space into the coordinates of this spacetime and vice versa, it's actually invertible, then you find that, first of all, indeed, this is not an isomorphism of the two manifolds. But what you find is that the metric of this spacetime is almost the same as the metric of Minkowski space. It differs only by a conformal prefactor. Namely, you see, if under that change of coordinates you transform the metric, you find that the Minkowski space metric is the metric of this other spacetime up to a factor phi, which is given by this expression. Again, the details don't really matter. What matters is that they differ only by a conformal prefactor, which means that they have the same causal structure. The actual distances between events will be very different. And what is a straight line in one may not be a straight line in others, except for light rays. They have to stay at 45 degrees. So what we have is that the two manifolds mg and m bar g bar have the same causal structure. Except that in Minkowski space, if you write it in the spherical coordinates, you have that the radius runs from 0 to infinity and that the time variable runs from minus infinity to plus infinity. But in this new space-time that is that has the same causal structure, we have that the variables have a different range, a compact range now. So the point of Penrose diagrams is to do this for all sorts of spacetimes that we might encounter, be they cosmological or spacetimes of black holes, and take those typically infinite-size spacetimes, find a transformation like that, so that we obtain a spacetime that has the same causal structure because it has the same metric up to a conformal factor, but a spacetime that is finite in size so that we can nicely draw it. In the case of Minkowski space, it's a bit of overkill, but let's do it anyway just to get started with this. So what we find here is that the range of variables is such now that in this barred manifold, it has the same causal structure, we have that the time variable has only a finite range, and the space variable, the radial variable, also has only finite range. It ranges only from here to there. we have that future infinity, future time-like infinity, is mapped to the point on top of this triangle. Future time-like, past time-like infinity is mapped to this point. We write it as little I plus and little I minus. The line of radius equal to 0 is this dotted line here. And a typical traveler would start over here and then travel that way. Could even be a geodesic, could be just sitting somewhere, and it will travel like this in this picture. This is a geodesic line. You see, it's just that everything is compressed in such a way that geodesics don't have to be straight lines now in this coordinate system, in this manifold with this coordinate system. So lines of constant radius, and I'm suppressing here the angular variables. So I'm only displaying the time variable up, and it's the t bar variable, and the radial variable, the r bar variable, in this direction. So this is space, this is time running from the past to the future. We have that points of equal radius are described like this, and lines of equal time are described like that, and so on. What about light rays? Well, light rays will travel at 45 degrees. Take an event somewhere here. Then if you send a light ray away from the origin of the coordinate system, then it will go at 45 degrees like this. If from here you send a light ray towards the origin of the coordinate system, it will travel at 45 degrees like that towards the origin. Remember, there's nothing special at the origin. It's just Minkowski space. But so there's no singularity or anything like that just yet. So from any event, if you travel outwards, you travel with the speed of light, you travel at 45 degrees like this. If you travel inwards, you travel at 45 degrees like that. If you have mass, then you'll have to travel within the light cone. So you will have to travel somewhere in this direction. You can't travel any flatter than this, any flatter than 45 degrees either way. And similarly for the past, your past light cone is always bounded by the 45 degrees. So the causal structure is easy to read off in this picture because this business about the angles stays the same, even though the actual lengths are, of course, very much distorted. What we see here is that a geodesic will always end up in that point. All geodesics all geodesics of massive particles will always end up in I plus and I minus. So any time-like path will, so not light-like, will end up over here in future infinity or come from I minus past infinity. But if you travel at the speed of light, or if you consider photons will not end up over here. Photons will end up on that line here, and they come from that line over here. This line here is called scribe plus. I think that's script I. It's usually called scribe, but I think it's just because it's usually written in some fancy font there. That probably Penrose first got to choose. So it's called scribe plus, script I plus. That's where light rays end up that are sent outwards, radially outwards, and this is where light rays come from. Now you could also end up yourself on that line. But for that purpose, you would have to keep accelerating so that you are eventually traveling with, asymptotically with the speed of light. And this way you can also yourself with a mass arrive over there. And I'll show you in a moment how that comes about. Okay, so in any case, the main point is that all of Minkowski space is inside that triangle. Also, the Minkowski space doesn't have any singularities, so I didn't draw any. But here's a legend, and the legend is that continuous lines like these will be infinities. So this is phi plus future light-like infinity. This is past light-like infinity. This is future time-like infinity. This is past time-like infinity. And by time-like, I mean could be traveled on, you arrive there on time-like paths. And singularities will be indicated by double lines.
What's the definition of future time-like infinity? Space-like infinity?
We will get to those in more detail. We will study those in great detail in coming lectures. For now, let's just say it's where, if you travel on a path whose tangent vectors are time-like, then you will end up there. So it's really about the tangent vectors of the path that you travel, where you end up then. Any path whose tangent vectors are time-like will take you to that point. So let's look at a few paths in there. These will be the paths, or these are the paths that are traveled by observers who are fixed at a position, at a fixed radius r. So somebody who is fixed at the radius r1 will travel through time and space in this way. It's always r1. This is r2, r3, r4, etc. So these curves are the world lines of observers who are just sitting there. They only travel in time, they don't travel in space. They have their radial coordinate fixed. But then look at this observer here. That observer is traveling just as usual, but then something happens. And what happens is that this fellow is accelerating. And when he's accelerating, then, you see, if he were to reach 45 degrees, he would reach the speed of light. Right? So he's accelerating. Let's say he's doing a constant acceleration or something like this. So he can actually hit that line over there. Right, now, the yellow really comes out very badly. Can you see that there is a light ray? A light ray would travel at 45 degrees. Yeah?
Did you say that the blue lines are travelers that are not traveling in the radial direction?
Yeah, they're not traveling at the radial direction. This is a line of constant R3.
Okay, but this axis is R, right? This, the horizontal axis is R, so what
Yes,
are
it
the
is.
lines curved then?
Yes, you see, well, remember that this is actually going up to infinity. Right? So the radius increases, and then it's infinite radius over there. Same here. If you travel like that, the radius is increasing to infinity. It's a very distorted coordinate system. It's a distorted coordinate system where constant radial values are given by those blue lines, and where constant time values are given by, lines like that. It's very distorted.
Excuse me?
Yep.
So for those blue lines, they can do lots of things in the direction, like perpendicular to the radial direction. For example, they can circle around.
Oh, yes, I'm not considering that at all.
And is it true that for any non-geodesic, they will always reach space-like infinity, even if they could travel like in the direction perpendicular to the radial
Well,
direction?
let me see. I haven't really thought about it in detail, but when I say that a light ray is traveling here at the 45 degrees, of course, if you have it travel in another direction perpendicular, in one of those directions that is indicated by the angles thing, you can lift that and you can make it a little steeper than the 45 degrees. But you can, of course, never make it flatter than the 45 degrees. Okay, so now we come to a very important definition, namely the definition of an observer's event horizon. So what's the event horizon of an observer? The event horizon of an observer, if the observer has an event horizon, not every observer has an event horizon, is the boundary of the past of this observer's future causal infinity. That's a handful, right? But it's not so difficult to understand what that means. Let's parse it. So take an observer, and what is this observer's future causal infinity? So if you are an observer, let's say you're sitting at R2, what's your future causal infinity? Well, future infinity is over there. And what is your past? Your past is the set of all those events that could possibly influence you. That's your past. And that is, in the case of Minkowski space, all of this. It's all of the Minkowski space. All of the events of the Minkowski space could influence you in the infinite future, which is the statement that if you wait long enough, you can get news from any part of the universe. You may have to wait an arbitrarily long time, but there's nothing that stays forever hidden from you in Minkowski space. If there was a part of the space-time that you will never, ever learn about, then the boundary of that region that you will never, ever learn about is your event horizon. Or more precisely, the boundary of the region that you will learn about, that is the event horizon. So in other words, the event horizon is the boundary of the set of those events that can possibly influence the observer. It's the boundary of the set of events that the observer can ever learn about. I have to give you an example to make this more concrete. Consider Friedmann-Lemaitre cosmologies. Let's say k is equal to 0 to keep things simple. In the case of such FRW or FL cosmologies, can one again find a conformally equivalent metric, a conformally equivalent space-time, just like we found for Minkowski space, the one with the bar on it, which was the same space-time except for a conformal prefactor, so it has the same causal structure? Well, yes, you can do it also for FRW cosmologies. And the details of the transformation are a little messy and no point in flashing them. You can find them, for example, listed in Hawking and Ellis' book in chapter 5.3. The result is, and you see it's much more instructive to look at the pictures than to look at the equations. The result is that for FRW spacetimes, we have this Penrose diagram. So there's a spacetime which is conformally, it's the same as an FRW spacetime except for conformal prefactors, so it has the same causal structure, but it is a finite size. Here, again, this dotted line is r equal to 0. Here we have future time like infinity. So if you are an observer with mass, and you are not going to forever accelerate and approach the speed of light, then you're going to end up over here in future time like infinity. If you're always traveling with a time like tangent vector, this is where you end up. If you choose to accelerate at some point, so you travel, all of these paths are within the future light cone, right? 45 degrees, they're all steeper than 45 degrees. Now, if you start accelerating and approaching speed of light, you have a chance. You can end up on scribe plus. Now let us look at an event. Let's call it P. Let's look at an event P and ask, what is its past light cone? Well, you see, all the events that are inside that light cone could have possibly affected P. But here, notice the double line, we have a singularity. It's an actual curvature singularity. It's not that just the metric looks odd, but the curvature goes to infinity. We will later analyze in much more detail what it means to have a singularity and what kinds of singularities there are. For now, let it suffice to say that we have a singularity here in this picture, in this space-time. And each event in our FRW space-time therefore has, in particular, a limit to how far back you can go. Right? There is a Big Bang at the beginning. I should say that not every FRW space-time has a Big Bang. For example, you could consider the a de Sitter universe, in which case you have an exponential expansion that goes on forever. But for example, the power law expansion that we discussed in a previous lecture would have a Big Bang. So what you see here is that if you go back to the Big Bang, to the beginning of that universe, you find that there's only a finite region of dependence. P depends only on this much. And that means that if this is, for example, today's lecture, and that is our space-time, then what this is telling us is that this triangle is all of the events in the universe, from the Big Bang to future infinity, all of the events in the universe, and we, sitting here now, can only possibly know about anything that happened in here. There's no way we could know anything about that happened in here or in here. The reason is simply that whatever happened in here might have sent a signal to us, but it would have to travel with the speed of light. And it cannot reach, an event from here cannot reach us there at the speed of light, because it would be flatter than 45 degrees. Same here. You know, if an event happens over here, it's technically earlier than what our lecture today, but a signal emitted from here to us would travel at 45 degrees. So it cannot hit us. We cannot know about it just yet. Therefore, we have a finite horizon. We see only that much of the universe. When we look out in the sky, we find that the universe is 13.8 billion years old, which means that we cannot see things that are 300 billion light years away, because whatever signal they sent to us had not enough time to reach us. Even if they sent it right at the Big Bang, it didn't have enough time to reach us yet. This horizon is called the particle horizon. It's our particle horizon. It's not the event horizon, it's our particle horizon. It's the maximum distance that things can be away from us that we can know about. And we can calculate how big our particle horizon is. It is not 13.8 billion light years. It's a little larger than that. And that's because while that signal has had 13.8 billion years to travel to us, during that time the universe expanded too. So whatever the sender of a signal right after the Big Bang sent the signal to us, it traveled 13.8 billion years, but in the meantime, you know, the universe expanded. That sender is now much further away from us than it was when sending out the message. So let's calculate how far away is the particle horizon at a given time t, such as today. So here again is, let's say this is our world line. We travel through the universe like this, and here is an event such as today, and here we calculate the past light cone in one direction. Then we want to know how big is that distance here.
So what defines the left-hand point of that?
Oh, here, us, just vertical.
Is the blue line a geodesic we run? Do you want to...
Yeah, well, yes, it could be a geodesic. I don't know. This is an astronaut here. Yeah. Yeah.
It's a very old astronaut.
Yes. Yeah, in fact, the true picture would be that, you know, there's a ball of stuff which then condenses and forms the astronaut. Remember, hydrogen is a colorless gas that, given enough time, turns into people. Okay, so how do we calculate the particle horizon? The metric of an FRW space-time can be given in this way. And R, the radial variable R here, is the co-moving radius. And that means that, for example, galaxies have the same radial coordinate over time. It doesn't change. Because we choose a coordinate system that grows with the universe. It's a co-moving coordinate system that grows with the universe. And that's convenient because then galaxies sit always at the same, numerically at the same value. Only if they have peculiar velocities, if they move in addition to the general flow of the expansion, if they move on top of that, then they will have a changing radial coordinate. And because the radial coordinate is co-moving, you know, we have this a squared factor here, which is telling that over time, a change dr, a change in radius, means more and more actual length because it gets multiplied with the scale factor. Early in the universe, a squared is small, and a dr means a small distance. Late in the universe, this is a large number, because of the expansion. This is a large number, and the same amount of dr now means a longer distance, right? So this is the co-moving distance here. Now, consider a light ray, this one. Consider a light ray which has this path. It has a time variable as a function of an affine parameter. It's just a parameter that parameterizes the geodesic of the light ray. That's the time the time coordinate as a function of the parameter alpha. That's the space, the radial space coordinate as a function of the parameter alpha. We know that the tangent vector is light-like, so tangent vector's length squared is equal to 0. Tangent vector is, you know, d gamma mu by d alpha. That's the tangent vector plugged into the metric equal to 0. So we have this relationship between d gamma 0 d alpha and d gamma 1 d alpha, just from requiring that this is the geodesic of a ray of light. And then we find that if we take the square root of this equation, we obtain this. You know, it could be in the one or the other direction. That's why you get a plus or a minus. That's the same equation here. Then we can divide through the d alpha, and we get the dr by dt is plus or minus, depending on which direction you travel, with the radius or against the radius, 1 over a of t. You may wonder, this is the speed, dr by dt. How come it seems to be slowing down over time? Isn't the speed of light always the same? Well, it is locally always the same, but remember that r is a co-moving distance. So over time, a change in r means more and more. So this is the speed of light in co-moving coordinates, in an expanding coordinate system. And if the r variable becomes larger and larger because you have a co-expanding coordinate system, then the actual speed of light, which is always the same, has to drop, of course, and that's how it does, with 1 over a of t. And of course, we choose this, as a matter of convention, we choose the scale factor to be equal to 1 at the present time. And then it makes no difference. Then the co-moving distance is the actual distance. And then that is the actual speed of light. Okay, so since the r by dt is given by 1 over a of t, the the particle horizon, the actual distance traveled by a ray of light, is then the integral from the starting time, which could be, for example, when the cosmic microwave background was emitted. So shortly after the Big Bang, those photons were emitted. We can basically say that this is equal to 0 or time equal to 0. And then 13.8 billion years later, that's us today. So we have to integrate that, and here is the scale factor. Right? We're just integrating up the speed over time. The velocity integrated over time gives us the distance. Right? This is dr by dt here, 1 over a. So this is what we obtain when we integrate that is the co-moving distance traveled from shortly after the Big Bang until today. It's a co-moving distance. But with the convention that the scale factor is 1 today, this is actually the distance. Because today the co-moving distance is the proper distance. And when you do this calculation with a reasonable assumption of what the scale factor did, you know, the various epochs of the universe, dark energy domination now, then previously matter domination, previously radiation domination, then you find that the particle horizon is about 40 billion light years, not 13.8, just because in the meantime the universe has also expanded. Now, how does the particle horizon relate to the event horizon? These are different things. Remember what the event horizon was. The event horizon is the boundary of the set of events that we will ever learn about. What we've just calculated is the boundary. We just calculated how far is the boundary away of the set of events that we can now learn about. And that's, you know, the set of events that we could possibly learn about today, that we could get messages from today. This set of events has a radius of about 40 billion light years. But if we waited forever, then we could learn from more events. In a few billion years, for example, the sphere of events that we can learn about will be much larger. Right? Because the sphere that we can learn about grows with the speed of light. And in addition, the universe grows, so you know, we learn about more and more over time. So the event horizon says, be patient, wait forever. And then, what is the set of events that you can possibly learn about in the universe? Can you learn about all events of in the universe? This would be the case in Minkowski space, no event horizon. In Minkowski space, you don't have an event horizon because if you are infinitely patient, you can get every message ever sent in the universe. No matter where somebody sends a message, I mean, like in a spherical, symmetric way, broadcast the message. No matter how far you're away from the sender, if you wait long enough, the message will reach you. But in an expanding space-time, that's not trivial. It's not clear that every message ever sent will make it to you, even if you wait long enough. Because it could be that the universe expands more at a faster rate between you and the sender than the rate at which the signal can cross space. So, all of this is just to say that if we have a cosmological event horizon, then it is the particle horizon that we will have at future infinity. The particle horizon is as much as we can see now. The event horizon is as much as we can see ever. It's the boundary of as much as we can see ever. So do we have a cosmological event horizon in our actual universe now? Well, for this, we have to calculate what this distance is, the co-moving distance. What is the co-moving distance of the furthest we can hear about if we wait forever. So we start at an initial time where messages are being broadcast, and then we integrate up the distance, the co-moving distance, all the way from that initial time to future infinity. And we ask, how much co-moving distance does this cover? How much co-moving distance does a light ray cross if you give it an infinite amount of time? Now it would seem, okay, in Minkowski space, if you give a light ray an infinite amount of time, it's going infinite distances, it goes anywhere you want. But in an expanding space-time, that's not necessarily so, because as I said, space-time is expanding, and it might be expanding faster than the speed with which light can cross distances. Okay, so the question is whether or not this integral converges or diverges. If the integral diverges, it means that there is no event horizon. It means that if you are infinitely patient, if you wait forever, then you can get light from anywhere, because light from anywhere will cross an infinite co-moving distance, infinite number of galaxies. You can go everywhere. But if it is convergent, if this integral is convergent in the space-time, then it means that light that travels forever will of course travel an infinite distance, an infinite number of kilometers. But the co-moving distance covered, the co-moving distance traveled, this is what we're calculating here, may be finite. The co-moving distance is the distance in a coordinate system that grows along with the universe. And if that co-moving distance is 100 or something, where, let's say, in units of the typical distance between galaxies, then it would mean that even if you wait forever, this light ray, light rays can only travel typically 100 galaxies across, even if you wait infinitely long. And that's because those galaxies are speeding away from each other at such a rate that light can't properly keep up. Even if you give it infinite amount of time, it can only travel past 100 galaxies, even though there are infinitely many more to go. And so therefore you can then not communicate, let's say, between galaxies that are 500 typical galaxy distances apart from another. Okay, so is this going to be convergent or divergent? Well, remember, we calculated the scale factor, and for various different epochs, an epoch being determined by the value of the W parameter. We found that the scale factor is given by this power law. Okay, let's plug that in there into that integral. It's this integral. And the question is, when is this convergent, when is this divergent? As you travel from, I mean, this really shouldn't be from zero, it should be from some finite starting point to infinity. So this, you see, if this is t to the power of something, let's say t to the power r, this is t to the power r, and r is larger than -1, then it's going to diverge. If it is r equal to -1, it's still divergent logarithmically. If the r is smaller than -1, then we have convergence. Okay, so we need that r is smaller than -1, which is to say that the threshold is linear growth of the scale factor, right? Because it's 1 over the scale factor. So if a of t is proportional to t to the power 1, which means here t to the power -1, that's the threshold. If the scale factor is just growing linearly, just coasting, then that's the threshold, it's divergent, and we don't have a horizon. If, however, it grows with a power that's a little larger than linear, arbitrarily little larger than linear, then this is convergent and we have an event horizon. We have a cosmological event horizon. But where is that? Where is that threshold? What is the critical W parameter? The relationship between pressure and energy density where this threshold happens. One moment, please. Well, remember, that threshold was at W equal to minus a third. If W is equal to minus a third, then we have here 1 minus a third, that is 2/3. Then we have 2/3 divided by 2/3, that's a 1. The minus, it's a minus 1. So the threshold is W is equal to minus 1/3. We had this as a threshold before. It's the threshold between inflation and not inflation. It's the threshold between acceleration and not acceleration. If W is anything smaller than minus 1/3, then the expansion of the universe is accelerating. Otherwise, it's decelerating. So what we see is that the existence or absence of an event horizon is in one-to-one correspondence to the universe being inflating, being accelerating.
So this might be a stupid question, but to calculate distance, shouldn't you be integrating with respect to r? And why is it the distance between two co-moving observers? You would think you would take the coefficient of the dr for the metric.
But what we do is we integrate the velocity over the time. Right? dr by dt integrated over t.
What's the formula for r in terms of t? I think
we had it up there. It's 1 over a.
It's 1 over a dt.
1 over a.
dr.
1 over a.
That answers my question. Sorry.
No problem. Okay, so how does that look like in pictures? How does it look like in terms of Penrose diagrams? Okay, so this is the case with an event horizon. That's a Penrose diagram for a space-time which has an event horizon. And you notice that the Penrose diagram has this relatively flat scribe plus here. That is why if you go as an observer to your future infinity and then look at your past, it's delineated by this yellow line, and you notice that everything that's outside that yellow line, everything that's in that patch here, you cannot know about. This is your event horizon, okay? Because any event that happened here can never reach you, right? Because it has to travel, any signal would have to travel at 45 degrees. So that is a situation of inflation with an event horizon. If you don't have an event horizon, for example, in a matter or radiation dominated universe, a universe that's always matter dominated or a universe that's always radiation dominated, then you would have that you travel to future infinity, you calculate your particle horizon as you're reaching future infinity, that gives you your event horizon, and you go 45 degrees, that's also the 45 degrees of the scribe plus. And so there is nothing outside. And you can learn about everything that ever happened in the universe by just waiting long enough.
So
yep.
If you're living in the left diagram and you're to the right of that yellow line, are you forced to hit scribe plus?
Well, if you're a beam of light, yeah.
No, if you're just a time-like observer, you just start off to the right of the...
No. You see, it's... no, you will be squeezed in there. You will be squeezed in there. You see, your forward light cone is 45 degrees. That's a 45 degrees. And so you travel like that, and yeah, you will be squeezed in there.
You have to travel. Well, no, if you travel at 45, it'll hit square plus. It'll stay parallel to the
that is right.
Yellow line will hit square plus.
That is right.
Baker.
I have to think about that.
It's not a global
Yeah.
event horizon. Something.
Sorry, what's the confusion?
If you start to the right of the yellow line,
Yeah.
then you can't get to
You will hit
time-like
square plus.
infinity.
Yeah.
You can't get to the future time-like infinity without traveling.
Well, the thing is, I plus is not actually part of your manifold. Nothing actually reaches there. So you would asymptotically reach it, and so everything can reach it. But like the inner light line doesn't, like the one that falls inwards will reach, like asymptotically reach it, but not actually reach it. And so you can still just follow along that inside line, and you'd be squeezed between Scry plus and the infalling light.
But you can't be squeezed because your future light cone will intersect Scry plus.
No, it won't.
It's tilted over more than 45 degrees.
What do you mean?
But
that's fine.
let us discuss that in the break, because I just want to squeeze in a bit of black holes before we get to that, before we get to the break. Okay, so for black holes we can do a similar thing. The metric of an eternal, non-rotating, uncharged classical black hole was first found by Schwarzschild exactly 100 years ago, in December of 2015. By the way, in November of 2015, Einstein was first giving a sequence of lectures where he first outlined general relativity. Okay, so here's the Schwarzschild solution in the Schwarzschild coordinates. It looks like it has a divergence in here, but that's just because of an unlucky choice of coordinates. You can choose other coordinates such as Kruskal coordinates and there won't be any divergence there. The metric and the curvature are fine there. This is where a horizon is, but there is no singularity there. Now, it's difficult to read off the causal structure of that space-time from the equations, and it took decades to figure it out. It's much easier to look at the Penrose diagrams. Now, it's very difficult to give for black holes the transformations that would map from realistic metrics to a Penrose diagram, because realistic metrics will be metrics that incorporate how the black hole formed. So here is the picture, and we don't really have good transformations that map that into actual solutions of the Einstein equations. So here we have again I minus, I plus, and now we have a singularity up here indicated by the double line. This is the surface. This line represents the surface of a star, which eventually collapses, and at this point reaches a point of no return. Here we have an event horizon. You see that this is the surface of the star. This is a traveler that watches what the star is doing, and that traveler is, however, doomed because he's foolishly following the star along too long. So he's now crossing that line here, that 45-degree line. If he had stayed outside that line, he would have hit I plus, and he would have noticed that this is his event horizon, because if you are here, you can learn about everything in your backwards light cone, which is 45 degrees this way, 45 degrees that way. Everything in here you can learn about, but this is the boundary of what you can learn about, so it's his event horizon there. But this doomed traveler was following the star along too much, crossed that event horizon, and then realized his mistake, tried to accelerate, going as steeply as he could this way, reaching almost 45 degrees, but has no way of getting out of it again because the event horizon here is at 45 degrees. So he will hit the singularity up here nevertheless. Notice that the singularity is actually space-like. For transformations that map between conformal diagrams and exact black hole solutions, you can refer, let me refer you to the text by Susskind and Lindsay. But they're usually not realistic black hole scenarios where you would have some sort of a gas of a star collapsing. The most realistic setup where you can actually calculate the formation of a black hole is that where you have an infalling ball of radiation, not of gas, but just a ball of radiation. And that too can eventually be so dense that it disappears behind its horizon. Much easier to calculate than the case of a gas. Right, and then before the break, let me show you the Penrose diagram for the case where the black hole eventually radiates away. So here again we have the surface of the star. We have the event horizon here. We have a doomed traveler. And from close to the event horizon, from a layer that's thought to be maybe just a Planck length thick, from the so-called stretched horizon, this is terminology from the quantum theory of black holes, which is on shaky ground. We expect that radiation is emanating from the horizon and makes it out, eventually diminishing the mass of the black hole so that the black hole eventually radiates away completely. And then we have this piece of space-time here, which is a piece of space-time without a black hole. It's just like ordinary Minkowski space, where this is in its past, but this part is just like ordinary Minkowski space. That piece here is absolutely not understood. And there's a huge controversy, for example, about the question whether or not the doomed traveler at the point where he or she is crossing the horizon will be fried or not. Classically, there's no reason to expect that this would be the case, but there are quantum arguments that would indicate that that might be happening. Right. Let me leave that up for the break. Okay, just a sec. Okay, we go to the break now. Let's say we take like 20 minutes, and in the meantime, let's have some food and discuss.